Okay, so just to review, we have had a little break, so I myself could not remember exactly what we were doing. Hi. So you naturally, I'm sure you know now what. So we have a metric space. Oh, what is this show? X is a metric space, F is a continuous or measurable map, mu is a probability measure. And we say that mu is invariant if, you know,
if mu, the inverse image.
Okay, this is the invariance, and we say that mu is ergodic if, it's a bit more difficult.
F minus A is equal to A only if mu the measure is 0 or 1.
Yes, so what it says is that every fully invariant measure, so if you remember I mentioned that if the map is not invertible, then F minus A is strictly stronger, F minus A equals A is strictly stronger than F of A equals A. Like it implies F of A equals A. So any map that satisfies this means that it's invariant, both all the pre-image of A belong to A and all the images of A belong to A. So this is a set that is fully invariant forward and backward. Any point that is innate stays innate forward and backward time. Every point that is not innate stays outside A forever, forward and backward timeline. So if you take a set that is fully invariant, then this must have 0 or full measure. Right? Mu A equals 0, or mu A equals 1. And so this, as I mentioned last time, it's a kind of saying that this system is indecomposable for the measure. Right? Because if you take any set that is fully invariant, if you found two sets that have positive measure, two sets that are fully invariant, both a positive measure, then the measure is not ergodic. Right? Okay with that? Yes? So what is the fundamental theorem? If you remember, we stated Birkhoff ergodic theorem. This is Birkhoff from the 1930s, a classical theorem that says that if mu is invariant and ergodic, okay, then, Carlos, what does it say? Don't read. Tell me if you know.
Asymptotically, the average.
The average of what? So we take every function f in L1 of mu, and for which initial conditions? For almost every initial condition. Remember, we had a discussion about that. It's a crucial point, right? Because you may have in a system different measures. So for mu, almost every x, okay, we have that the limit of 1 over n of the sum of the averages of fi of x as n tends to infinity converges exactly to the integral of phi d mu. Okay, so this integral, this left-hand side depends on the point, whereas the right-hand side does not depend on the point, it just depends on the function. It's the average value of the function with respect to that measure. In various dynamical systems, you might have many different measures, and therefore they will give different integrals, right? But the measure does not appear on the left-hand side, right? So the measure appears on the right-hand side, and the initial condition appears on the left-hand side. This is linking these two things that are have independent definitions, right? If you take a different measure, you will get a different value for phi in general, and this means that the points, this limit will converge to a different value, okay? That's why this cannot be for every x. It needs to be for mu almost every x. So this is for the points that are related to the set mu, to mu. Any questions on this? This is really the fundamental fundamental definitions and the fundamental theorem of ergodic theory. So later on we will do a little bit of general theory. You can see the ergodic measures as extremal measures in the space of invariant measures, but we will look at that a bit later. What I prefer to do now is look at the problem of proving ergodicity. So if you want to apply this theorem to a specific dynamical system and to a specific measure, then you need to show that that measure is invariant and ergodic. Okay? And I think we did several examples of measures that were ergodic. Is that right? For example, the Dirac delta on a fixed point is ergodic. The Dirac delta shared out amongst the points of a periodic point is also ergodic. Maybe that was an exercise, maybe that I gave you. And do you remember the example of a map that was where the Lebesgue measure was not ergodic? Yes, so we had an example where you clearly have two ergodic components for the Lebesgue measure. And in general, we have two situations. Either the measure is kind of a trivial measure, because if you take a measure that is the Dirac delta on the fixed point, then this theorem does not give you much information. Right? You remember? Yeah. Okay. Why does it not give you much information if mu is just a Dirac delta on a fixed point?
Mu is Dirac delta, so you cannot just about one point, just in measure. If set is contains that point, then the integral is 1.
Yes.
And
but this theorem still applies, right? If the Dirac delta is a Dirac delta, mu is a Dirac delta on a fixed point, then this is still true. Then it gives you that the limit of this is equal to the integral of phi for the Dirac delta, which is just the value of phi at that point, right? So what do we conclude if mu is the Dirac delta at one point? What does this theorem tell us? So let me make a remark actually here because it's important. If p is a fixed point, so if f of p equals p and mu is equal to the Dirac delta of p, okay, then mu p is invariant and ergodic. Then mu is invariant and ergodic. Okay? So this means that the limit of 1 over n, the sum, so for all phi in A1, mu, the limit of phi composed with fi of x, I equals 0 to infinity, equals the integral of phi d mu, which is the integral of phi d delta p, which is phi of p. Right? So it's phi of p. Whatever the value of phi of p is. So remember we looked at the example where we have so our map 10x mod 1. Okay, so we already went through this, but this is a key point and I want to make sure this is clear. And we have, for example, let p is equal to 0.2 repeated. Remember, this is a fixed point. Yes, somewhere here. And so we take two measures. We take mu equals delta p, and we take 2, is mu equals Lebesgue measure. Okay? So we will prove today that Lebesgue measure is ergodic. We've already proved that it's invariant. So let me write this theorem on the board, but before we prove it, let's look at the consequences of it, some of the consequences. So theorem, let f of x equals 10x by 1, okay? Then the Lebesgue is invariant and ergodic. Okay, but before we prove that, I just want to get a little bit to digest the meaning of these things. So here we have Birkhoff's ergodic theorem. Okay, using this theorem, we have at least 2 ergodic invariant measures here. Okay? So this is 0, 1. This is the point P equals 0.2 periodic. So when we take some phi, this integral will be different, of course, depending on whether you take. Unless phi is constant, okay, we have some phi, okay, whatever this is, phi. I'm using this as a graph of phi as well as a graph of the function, okay? And then if we take, for example, if we take some orbit here, x, okay, then the average of value of phi along that orbit will converge to the average value of phi with respect to the Lebesgue measure. Right? But if we choose delta p, then this theorem says that this limit will converge to the average value of phi with respect to mu p, which is just equal to phi of p. But those might be different. So is there a contradiction here? Is my question clear? Is the contradiction clear or not? Do you understand?
We have a statement almost zero, because in Dirac measure almost zero, it means that just point P. Right?
Is that clear? Is that clear? Yes, that clear? So we have this, right? Okay? So in the case in which we have the delta P measure, then what set, then this means that there may be a set. So what almost everywhere means is that there may be a set where this does not hold, but this set has 0 measure. Okay? So in this case, if you take, notice that in this case delta P of the whole interval minus the point P has 0 measure. Okay? So when we take a measure that is a Dirac delta, the Birkhoff ergodic theorem only tells us a conclusion which is kind of trivial because it only tells us the conclusion for the point P. So Birkhoff's ergodic theorem has its limitations depending on the measure. Right? If the measure is a Dirac delta, then the conclusion applies to very few points. If the measure is Lebesgue measure, then it applies to Lebesgue almost every point, depending what measure we're interested. So I'm really just trying to emphasize this, that Birkhoff's ergodic theorem contains a measure and it could not be otherwise, because if you have a measure on the right-hand side and you do not have a measure on this left-hand side, then this can only hold if you say, okay, this only holds for a set of points of full mu measure, but it may not hold for points in a set that has 0 measure. So in general, the point of view that in some sense Lebesgue is the reference measure of your space leads us to think that we are particularly interested in studying Lebesgue measure. This is the kind of the point of view we'll take in this course. But I would like to say that there are many other measures that are of interest, and today we're also going to show that for this map there are many other measures that are interesting that are not Lebesgue measure and that are not Dirac delta measures. So there is more measures that may be very interesting. Okay? But in some sense what we want is the general emphasis is on Lebesgue measure and measures, as we shall see, that might be equivalent to Lebesgue measures. We shall see later on in the course. So we know already that Lebesgue measure is invariant, right? We proved that that is easy. And so the key point will be to show that it is ergodic. So how do you show ergodicity? Okay, so proof. So how do you show ergodicity? How do we set up this proof?
You have to take a set A if inverse f minus A is equal to A. In this case, we need to prove the measure is 0 or 1.
Right. So we start with saying, okay, because the definition involves sets like this. It says if a set satisfies this property, then it satisfies a certain condition. It has measure 0 or 1. Okay? So we're going to assume that it has positive measure and prove that it has full measure. If it has positive measure, it must have full measure. Okay? That f with Lebesgue measure of A is positive. If it has 0 measure, there's nothing we can do. Okay? So we want to show, we will show that necessarily Lebesgue measure of A equals 1. In fact, we will show that the Lebesgue measure of the complement of A is equal to 0, which is the same thing. Okay, so the first observation.
Can we use approximation by intervals? For example, if Lebesgue measure is positive, so in this case there is some interval. It's A is more than dense in interval, like in A, like interval. We can take interval, and we know mode 10x is expanding, right? So inverse image of interval, of course, length smaller than our integral. So it's a contradiction to our statement.
Yes. Well, your argument was not complete, but essentially that is the way we'll go. Yes, exactly. So can anyone else fill in the details?
Yeah.
Yeah? Have you read the proof already?
No.
You just know the proof. So let's see. Okay. So the first observation. So which intervals do we want to approximate it? So we will use the fact. So we're going to use the fact that we have a partition here. Sorry. So actually I want to prove this in a little bit more generality. I'm sorry about this. I don't want to prove it for just 10x mod 1. I want to prove it for any piecewise affine full branch map. So let's do it, because otherwise it's really very limited. So I'm sorry. Let f be a piecewise affine full branch map. So remember that this means, for example, it can be this, something like that. Okay? Even countable number of branches, okay? Full branch piecewise affine map can have a countable number of branches, infinitely many branches, as long as each one the map is affine. So the derivative is constant on each branch. Okay? And one of the exercises I gave you is to show that Lebesgue measure is invariant in that case. Okay, so we will leave that aside. That's an exercise you can do. In the case of 10x mod 1, it's easy. In this case, it's also relatively easy. In the countable case, you need to have an idea. Okay? So we will leave the invariance and just concentrate on the ergodicity. So part of this definition is that we have a partition which I would call, remember the definition is that there exists a partition P, let's call it P into intervals omega intervals, such that f from omega to 0, 1 is a affine bijection. So omega, we can call them maybe omega I. Okay, so this is, for example, this is omega 1, this here is omega 2, and this is omega 3. Okay, this is the definition of what we start from. Okay, now if you remember, when we were doing the topological study of these piecewise affine maps, we noticed that if you look at the second iter of the map, what does the second iter of the map look like? If we have here 3 intervals, yeah, if you remember, then we have the 3 intervals, copies of the 3 intervals here, omega 1, omega 2, omega 3, and then you can divide each omega into 3 subintervals, each one which maps to omega 1, this one maps to omega 2, this one maps to omega 3, and the same for all the other ones. Okay, so the second iter of the map is also piecewise affine map that has a collection of intervals, right, that map after second iter onto 0, 1. So we let P1 equals P, okay, then there exists partition P2, okay, is equal to omega 2i, okay, such that f2 from omega I2 to 0, 1 is affine bijection. Okay, and then you can continue this process, right? And notice that P2 is a refinement of P1, right? P2 is a refinement of P1 in the sense that the elements of P2 are all subintervals of each element of P1. So these are the 3 elements of the partition P1. Okay, I can write this as omega 1i. Okay, they're the same elements, but now I index them with 1 because I'm going to build a sequence of partitions. And so here I have P2, and I can keep doing it, right? So Pn is equal to some partition omega ni, okay? And Fn from omega ni to 0, 1 is an affine bijection. Okay? And if you remember, we also did some calculation about the size of these intervals, right? Because it's an affine bijection, the derivative must be bigger than 1 everywhere, and these are shrinking. Okay? So notice that omega, the size of these intervals, let me just write it in words, size of intervals omega and I is going to 0 as n tends to infinity. Right? So if you take larger and larger iterates, you take smaller and smaller elements of the partition. Each one of them maps bijectively. Okay? So, as you said, since we have a set of positive measure, okay, then there is a theorem called the Lebesgue density theorem, which I don't know if you all know. Do you know the Lebesgue density theorem?
Yeah,
This,
you
did it.
Analyze this a little bit. We have some homeworks and just professor gives us.
Okay, okay. So the Lebesgue density theorem says that if you have any set of positive measure, then almost every point in that set is a Lebesgue density point, which means that if you take a very small neighborhood of that point, most of the measure belongs to that set. So this is kind of, in some sense it seems obvious, but it's, I think it's kind of not completely obvious, because if you have suppose you have a set, a very complicated set, which measure 1/2, right? Then you could say, okay, let me take a subinterval of my space, a subdivision of my space, and maybe also in that subinterval, half of the measure belongs to A and half does not belong to A. And let me take a smaller region, and maybe always you can take sets where half of the set belongs to A and half does not belong to A. Okay? So in some sense you can say, well, the formulation, the statement that this set A has measure 1/2 says that half of your space belongs to A, and maybe that continues to be true at all scales, right? If you go down, if you go to a very small scale, maybe you still have at that scale, you take all this, you split it up into lots of little sets, and for every set, half of that set belongs to A, half does not. And this Lebesgue density theorem says that this is not true, right? That if you go to very small scale, you go to very small intervals, either 99% of that interval, of that set, belongs to A, or 99% does not belong to A. Right? So it's kind of saying that at a very small scale, the measure is concentrated in some way, necessarily. Okay? So this is the Lebesgue density theorem for A, and how do we apply it to this? So this implies, so since Lebesgue measure of A is 0, okay, I will just say by Lebesgue density theorem, for all epsilon greater than 0, so for by Lebesgue density theorem, for all epsilon greater than 0, there exists some n greater than or equal to 1 and some omega n I in Pn such that the Lebesgue measure of A intersection omega ni divided by the Lebesgue measure of omega ni, in other words, the relative measure of A inside omega ni, is greater than or equal to epsilon. Greater than or equal to 1 minus epsilon. Almost close to 1. Okay? So, what we're saying is that we have here a set of positive measure. So now we know that we have this sequence of partitions whose elements are becoming arbitrarily small. So for any epsilon, okay, Lebesgue density theorem that says almost every point of A is a Lebesgue density point. Okay? So we now have a partition with 1,000,000 tiny little intervals, okay? If we want, we can go down further and go to 1 billion, okay? And one of them will be so small that it will contain a Lebesgue density point of A, and 99% or whatever, however much proportion of that measure belongs to A. Okay, so we've gone down to small scale. So this uses the full branch property very much. Okay, because the full branch property is what gives us this very nice structure that tells us that we all, well, we will use the full branch several times actually. We've not yet fully, the full branch tells us that always each of these maps to 0, 1, but in particular it gives us the structure of these refined partition elements here. Yes, actually for this step we just use the fact that we have partition elements whose width go to 0. In a moment we're going to use the fact that these map to 0, 1. So for the moment we've just used this and we found one of these. Okay? And then the next step is that, let us write this. So let me write here subscript epsilon to remind ourselves that we've chosen this in terms of epsilon. Right? If we choose epsilon smaller, we might need to go to smaller partition elements, so we might need to take a bigger n epsilon. And, okay. So let me write this. Of course, this means that the complement of A has small measure. Okay, let me write this as the Lebesgue measure of the complement of A intersection omega n I over Lebesgue of omega n I is less than epsilon. Okay, that's just the same thing. Now we use the fact that Fn from omega ni to 0, 1 is an affine bijection. Okay, so this means that we have here omega n I, and then here we have Fn, and then here we have 0, 1. Okay, and here we have subset A complement intersection omega ni. So it's a very small set. It has measure less than epsilon, but it's inside here. Okay, and the fact that it's affine, and this is where we use the fact that it's affine in a crucial way, because later we're going to look at we're going to try to relax, because this is a very strong assumption, right? But the fact that it's affine, the fact that it's full branch means that it maps surjectively onto 0, 1, and the fact that it's affine means that every set is stretched by exactly the same amount. So the proportion of this inside here is the same as the proportion. Here you have the image of that, so you have the image Fn of AC intersection omega ni. Okay, and so is an affine bijection, and so the proportion, the Lebesgue measure of Fn of AC intersection omega ni over the Lebesgue measure of Fn of omega ni is equal to this proportion of omega AC intersection omega ni over the Lebesgue measure of omega ni. Okay, so the proportion of the measures of the two sets is preserved because it's just an affine stretching, and as we said, this is less than or equal to epsilon. Okay, so okay, now just one more observation that we need. Moreover, recall that, notice that F minus A equals A implies F minus 1 of A complement equals A complement. Remember, I mentioned this, okay? And this implies that F minus n of A complement is also equal to A complement, okay? And therefore, omega n I of A complement intersection omega n I is equal to, I can write AC as Fn of F minus n AC intersected intersected omega n I. Okay, because AC is the same as F minus n AC, and this is equal to AC. This is equal to. So we take Fn. We can distribute this intersection. So this is just equal to AC intersection Fn of omega ni. And what is Fn of omega ni? Is the interval 0, 1. So that's the whole space. So this is just equal to AC. I mean, intuitively, if you think about it, this is kind of obvious what this is saying, right? It's saying that we've defined A, we've got AC, the complement of A is a subset of 0, 1, right? And you can look at the pre-images of AC. The nth pre-image of AC is equal to AC, okay? And therefore, the restriction of AC to omega in, which is what this is. This is AC intersection omega in. When you take when you map this by Fn, it will give you all of AC here. I mean, you can convince yourself that this has to be the case, but this is just the formal algebra that shows this. Okay, so when you take the restriction of AC to omega ni and you apply it by this full branch, then you get this restriction. The image of this restriction is all of AC. That's what this is saying. Okay, and then therefore this is easy to conclude. So therefore from here we get that the Lebesgue, okay, so Lebesgue here, Lebesgue of Fn of AC intersection omega and I over Lebesgue of omega and I is equal to what we just wrote here. This is actually equal to AC, Lebesgue of AC, Lebesgue of AC, and this here is equal to Lebesgue of Fn of omega ni, right? Because I'm copying this down. So Fn of omega I is the whole interval, right? So this is just equal to Lebesgue of AC. Okay, and this we said is less than or equal to epsilon. Since epsilon is arbitrary, it means that AC has 0 value, because you can do this for every epsilon. So, in some sense, the crucial property here is the structure of the full branch maps, which gives us all these partition elements, and the affine property, which we have used here. Okay? Here we've used affine. Because we've said that this proportion is equal to this proportion. Okay? I just want to point this out because maybe the next lecture, the one before, we're going to prove a generalization of this theorem that shows that you don't need affine, okay? You can also have some maps which is not affine, okay? And the key observation is that we don't really need an equality here. What do we need? We just need an inequality, okay? Because what we need is to show that this is less than or equal to epsilon, okay? In fact, what we need is, so here, we just actually need less than or equal to some constant times this, okay? We don't even need just this to be less than or equal to this, but we need less than or equal to be some constant times this for a constant that doesn't depend on n, if it's just some uniform constant. Because then we can still, we will get a constant here, c epsilon, but we can still make that arbitrarily small by taking epsilon. Okay, this is something we're going to do in a little while, and we're going to generalize this. Okay, but this proves the ergodicity of Lebesgue measure. So in this case, it is relatively simple argument. In general cases, it's really non-trivial to prove ergodicity of Lebesgue measure. Sometimes it's false. Any questions? Okay, so what I want to do for the rest of the class is just to give two examples, two applications of this theorem. Okay, one of them is very simple, and maybe I discussed it before. And it's actually an application in number theory. So maybe I mentioned that ergodic theory has a lot of interesting corollaries and applications in number theory. And an almost immediate corollary of this is that Lebesgue, almost every x in 0, 1 is normal in every base. So I will say what I mean here. First of all, do you know what it means to write a number in base 3 or base 4? Right? So x, so when we usually write the decimal expansion of x equals in base 10, so in base 10, right, when we write x equals 0.37154, what we really mean is that x is equal to 3 over 10 plus 7 over 100 plus 1 over 1000 and so on. Okay, this is the base. And in general, you can use this for every integer k, for any k in n. Okay, k greater than or equal to 2. We can write x equals x1 over k plus x2 over k squared plus x3 over k cubed and so on. Okay, so for example, in base 2, e.g. k equals to, and here we have the digits. Okay, so here we have xi is one of 10 digits, and here we have that xi is between 0 and k minus 1 digits you use for this. Okay, for in case 2, we write x equals x1 over 2 plus x2 over 2 squared plus x3 over 2 cubed and so on, where xi can be either 0 or 1. This is the base k representation of the numbers.
Sorry, what's the mean normal?
Yes, so now I'm going to define. So we say that normal, so definition, so x is normal in base k if the asymptotic frequency of each digit in the base k expansion is equal to 1 over k. So the asymptotic frequency means IE, if you take x equals 0.x1, x2, x3, x4, right? And then you let, so you take 1 over n times the cardinality of I between 1 and n of xi equals to d the limit as n comes to infinity is equal to 1 over k for all d in 0 to k minus 1. So for every digit in 0 to k minus 1, which are the digits that are allowed to appear in the base k expansion, so this is the base k expansion, and then you look at the base k expansion, right, and you look at how many times the digit d appears. Okay, this is exactly like the dynamical frequency of the points. You look at how many times the base k, the expansion appears, and you look at the proportion in the first n of how many times it appears, and in the limit is exactly 1 over k. Okay, so a point is normal in base 10 in decimal expansion if each digit appears 1/10 of the time. Okay, asymptotically, not exactly. So you look at the first 1 million digits and you might have all of them once. Okay, but asymptotically, if you go to infinity, then you see that the digit 0, the digit 1, and every digit appears 1/10 of the time. Okay, so in the base 10 expansion, it's easy to see that some points have are normal. We can construct one. Okay, we can just put 0, 1, 2 up to 9, 0, 1 up to 9, and we can repeat that, and each digit appears once. Okay, it's easy to construct digits that are not normal in base 10. For example, if a digit never contains the digit 5, if a number, if the decimal expansion never contains the digit 5, then it cannot be normal in that digit. Okay, so what this corollary is saying, and we're going to prove it now, it's a simple corollary of Birkhoff's ergodic theorem, is that almost every digit is normal in every base. So let's think about that statement a second. So first of all, let's prove that almost every digit is normal in base 10. Or let's think of it in base 10. So let me write it like this. Let nk equals the set of x which are normal in base k. Okay, then the set of points which is normal in every base, and let n equals the intersection for all k greater than or equal to 2 of nk. The intersection. So these are the points that are normal in every base. Okay, this is equal to the set of points x normal in every base. So it is sufficient to show that each nk has full measure. Okay, why is that? If we can show that each nk has full measure, so if we can show that almost every point is normal in base k, and we can do that for every k, why does that imply that the intersection still has full measure?
Because union is full measure, right? We can take just 2 if we take, for example, n2 and n3, so intersection again full measure.
Why does the intersection have full measure?
Because the measure of intersection is equal to measure of sum of two sets and minus union.
Minus the union of the complements.
Yeah.
The complements, right? Because okay, I will leave that as an exercise. So enough enough to show that the big measure of Nk is equal to 1 for all k greater than or equal to 2. Okay, it's a simple exercise to show that this implies this, yes, because the intersection of these measures is the set minus, because the complement of each one has 0 measure, so the union of the complements has 0 measure. That's the simplest way to say it. Yeah, because it's a countable union of sets of 0 measures, so the union of the complements, so now you take 0, 1, you remove the union of the complements, and you're left with something that is the intersection. Okay, just make sure you do that little exercise. Okay, so we just need to show that each one of this is normal in base k. So what does Birkhoff's ergodic theory, what does the invariance, what does this theorem have to do with this?
I think we need to choose a base phi t.
Yes. So let's choose a base. Let's choose base 10, just to simplify things for the moment, okay? Start with k equals 10, because we're more familiar with it. So how are we going to show that the big measure of the set of points that is normal in base 10 has full measure? Carlos, you had some suggestion? We want to use dynamics. So we want to use this theorem, the fact that 10x mod 1, so we know that, so let's consider f of x equals 10x mod 1. Okay, so remember we had 10x mod 1, and we had here 0.1, 0.2, 0.3. We have this partition, right? And we have this map looks like this, right? And this is piecewise affine. So Lebesgue measure is invariant and ergodic, right? And therefore, so remember that there was a connection between the decimal expansion and the position here. What was that connection? No, the connection just in this map. So if x is equal to 0.3714, I don't know why I always end up with the same number. Okay, then if x naught equals, well, if x is this, right, then we have that, then we know that this point here belongs to this element of the partition. So we can, let's index these elements of the partition by I, or by omega 0, omega 1, omega 2, all the way up to omega 9, right? And every number begins with decimal 0 if it be, or 1 or 2 or 3, depending on which element of the partition it's in, right? So if you have a number that's in omega 0, then its decimal expansion will start with 0. If you have a point in omega 1, its decimal expansion will start with 1, and so on, right? So here, once you know the decimal expansion, you know that this is in omega 3, and then you know that f of x, which is equal to 0.71428, is in omega 7, okay, and so on. f2 of x will start with 1, so it will belong to omega 1, right? So the decimal expansion tells you exactly where the images of all the points will belong to according to this partition, okay? And similarly, if you know the frequency of visits to one of this partition, so you look at omega 6, whatever, okay? This is omega 6, and this value that we're calculating here, it is, sorry, the asymptotic frequency of the occurrence of the digit 6 in the decimal expansion is exactly the same as the asymptotic frequency of visits of the map to omega 6. Is that clear? Yes? So you can measure the same thing. So this map, 10x mod 1, is especially suited, in some sense, it's designed to look at the decimal expansion. Okay? Because for this particular map, we have this natural partition into 10, and which of the elements of the partition will tell you exactly how many times you fall, will tell you exactly what the occurrence of the digits is. Okay? So by Birkhoff's ergodic theorem, okay, so letting phi equal to one of these intervals, say omega I, okay, which is equal to 0.I to 0.I plus 1, open, okay, this is one of the partition elements, then 1 over n, the sum of phi composed with fi of x, I equals 0 to n minus 1, converges to the integral. This is just the, this is the characteristic function, the characteristic function of omega I, which is equal to the characteristic function of this set here. So this is equal to the integral of this, of phi dV, which is just equal to 1 over 10. Okay, because it's the characteristic function of this. Okay, and this is exactly equal to 1 over n times the sum times the number of indices I equals 1 to n, such that, okay, this is exactly equal to the indices I equals 0. I'm using slightly different boundaries here, but when fi of x belongs to omega I, okay, and this is exactly all the times that fi of x belongs to omega j, and j here in omega I, okay, and every time fj of x belongs to here, that corresponds to having an I in the decimal expansion. Okay, and so for the general case, how do we do the base 2, for example? Okay, it's exactly the same thing. For base 2, or for base k, consider the map fx equals kx mod 1. Okay, and why does that give us exactly the same thing? So here we have, for example, for k equals 3, we have 3 elements, so the map will look like this. Okay, and then we write some point x is equal to x1 over 3 plus x2 over 3 squared plus x3 over 3 cubed, and so on, right? And then what is the effect of applying f of x? F of x is equal to 3x mod 1, okay, is equal to 3x mod 1. This is equal to 3 times x1 over 3 plus x2 over 3 squared plus x3 over 3 cubed, and so on, right? And when you multiply by 3, this gives x1 plus x2 over 3 plus x3 over 3 squared, and so on, right? But this is mod 1. So x1 is an integer, right? So we drop x1, and this just gives x2 over 3 plus x3 over 3 squared, and so on, right? And so you see that the expansion of f of x in base 3 is just, so when you take f of x, the expansion of whatever point you get is just a shift of the original expansion here, right? We have an infinite sequence. Here it's x1, x2, x3, and here it's x2, x3, x4, and so on. So it's exactly like it works with the decimal expansion. Decimal expansion, you multiply by 10, you just shift, and when you take the base 3 expansion, you multiply by 3 and you just shift. Okay? And that corresponds to the fact that we have that the base 3 expansion, so because of this, okay, this means that the base 3 expansion can be recovered, has the same structure as the 10x here. So here we have 3 elements, omega 0, omega 1, omega 2, right? This is 1/3 here, this is 2/3. And if you think about the way the base 3 expansion is constructed, you see that xi here can be either 0 or 1 or 2. There's 3 possibilities, right? And if x1 is 0, okay, this means that this cannot be bigger, the remaining sum cannot be bigger than 1/3, right? So it means that this whole point is going to be here, less than 1/3, if x1 is 0. If x1 is 1, then this has to be between 1/3 and 2/3, because the sum of this remaining part is bounded by 1/3, right? So the contribution of this remaining part is 1/3, and if x1 is 2, then it's going to be here, because it's going to be 2/3 plus something else, okay? So again, in exactly the same way, when you have the base 3 expansion, then the first digit of the expansion will tell you which one of these you are in, okay? Then when you apply the map, you shift once, okay, and you get this new expansion. So this means that now the position of f of x is determined inside this partition, is determined by x2. That's going to be again 0, 1, and 2, which means that if you look at the original expansion, then you look at all the digits in the original expansion, and they tell you exactly where you are inside this partition, omega 1, omega 2, omega 3. Okay? And by Birkhoff's ergodic theorem, almost every point spends how much time in each of these elements here? 1/3. Okay? Because this is again a piecewise affine map. Lebesgue measure is ergodic and invariant for this map. And so each point spends 1/3 of the time inside.
But however, we can construct as much elements we want, but they not goes to this interval. So
Sorry, say again.
that we can, knowing this, we can construct a lot of initial points that don't enter to this interval.
Absolutely. Absolutely. So you mean, so what are you saying? That we can construct lots of points that never go in here? Because if you look at the base 3 expansion and you do not have a 1 anywhere, then the point will stay here and here always.
But measure 0.
Sorry?
But
But we'll have measure 0. Yes.
There is no 1 measure 0, because we have just 2 choices.
Well, because by Birkhoff's ergodic theorem, you know, we know that almost every point, almost every point has 1/3 of each digit. So the set of points that are not normal in base 3 has 0 Lebesgue measure. Okay? And we can do that for base 2, base 3, base 4. For every base, it's exactly the same argument. Okay? For every base, we show that this holds. I will not do it now, but it's pretty clear. You write this in base k, you apply the mapping kx mod 1. Okay? Sorry, here I ended up writing the case of k equals 3 as an example, but you can do everything for general k and you get exactly the same. Okay? So for the general case k. So the conclusion, which is quite remarkable, notice that these are different maps, like they really are different maps. It's not like we're looking at the same map in different ways. We're looking at the same set of numbers, right? We're looking at the same set of numbers, but 3x mod 1 is a completely different map from 10x mod 1. When you take a point here and you multiply by 3, the multiplication does not depend on the base, right? When you take a number and you multiply it, 3 times that number is 3 times that number. The base is just one way to represent the number. We shouldn't make a confusion between the base representation. That's why it's called representation of the number. So the same number you can write with a decimal representation, base 3 representation, base 4, any base representation. Okay? And it just so happens that if we write the base 3 representation, then to prove that almost every point is normal in base 3, it is useful to use the map fx equals 3x mod 1, and then we can apply Birkhoff's ergodic theorem and we can get our conclusion. It's our choice to use the map kx mod 1 to prove that the numbers in base k are normal. Okay. So, as a curious, so I don't think I will have time to do the second application I wanted to do. But let me first make this remark that I don't think anybody knows one example of one number in this set that is normal in every base. Right? So, Lebesgue almost every point is normal in every base, but as far as I know, we don't know any example. There's no immediate relationship between the base representation of a number in base 2 or in base 3. In general, you take a number that is normal in base 10, there's no reason why that number should be normal in base 3. So when we do the argument, when we do this intersection, we're really doing this intersection. I mean, the sets of points that are not normal in base 2 might be a completely different set from the set of points that are not normal in base 3, in base 4, and so on. You're really taking the union of a set of points, a countable set of points, but all of them have zero measure, so the union has zero measure. So we conclude that almost every point is normal in every base, but we don't know any of them, any one of them. This is a very curious and intriguing question. Okay, so maybe since you have, as you said, a very hectic day, and let me just, instead of doing the other example, I will do it next time, but just a remark to related to what you said. So if you take the set of points that have that do not have a 1, okay? What is the structure of this set of points?
In base 3?
In base 3, for example, yes.
We don't have 1, so it's like counter set.
It will be a counter set, okay? It's not completely obvious, but it will be a counter set, but it's the same construction that we did before, because what are you doing? You're deleting this set, right? And then, so none of these points belong to your set. And then obviously you're deleting the set that maps to this, which are all the points whose second digit is 1, right? And then you get 3 of these, and then here you get points whose first and second digits are not 1, but inside you get a set of points whose third digit is 1, and so on. And you go and you delete all those. Okay? But in some sense, inside here, there is, there's an uncountable set of points whose sequences contain all possible sequences of 1 and 2. Right? So, if here we have x mod 1, right? Then it's natural to code all these points by the binary representation, or by 0 and 1. So here you have 0, here you have 1, okay? So here every point is coded between 0 and 1, and in some sense, okay, there's a bit of a problem with the boundaries, remember, we discussed that in some detail, but let's not worry about that for the moment. In some sense, you can associate to each of these points one of these points of the Cantor set that is here, right? So there's some interesting, it's like within this set, there are lots of other invariant subsets, okay? And that's the basis for the next example that we'll talk about, which is very interesting, but in particular in here, if you remove the digit 6, it also gives you a Cantor set, which is a set of all points that don't contain 6, right? Or you can delete 2, and you get another counter set that is all the points that do not contain 2, right? Or you can just delete the points that have this block of 2 digits, right? And then this will be some small interval here, and then lots of small intervals which will also give you a counter set, right? You may have 2, you may have 6, but you never have 6 after 2. You may never have that combination of 2 digits. Okay? And that also, if you think about it, is a dense set. It's another way to see that it's a counter set is you see that inside any interval, there will be a subinterval of points that have 2, 6 in there. Right? Because if you take any 2 points, then if you look at these 2 points, they will be the same, the decimal expansion. If they're very, very close, then maybe the first 1 million digits of the decimal expansions will be the same. But after that, you will have all possible combinations again. Right? So inside that interval means you're fixing the first 1 million digits, but then all these points is like a micro version of the whole interval again, right? Because once you fix those 1 million digits, you have all possible combinations. So here you will have lots of points that contain the digits 2, 6. So if you delete them, you will delete some more intervals. So there's a dense set of subintervals that contain the digit 2, 6. So what's left is a counter set. Yeah. Okay. So this is just to get a feeling for how rich the dynamics is and how rich the structure of real numbers is, actually. Because all we're saying is that all these dynamics, these are also nice examples because they depend on nothing except the structure of real numbers, right? And the structure of real numbers is very, very rich, as we can see from something like this. And this is nice because this is really first example of a theorem in number theory. There's no dynamics in this statement here, just to do with number theory, base representation, but the proof uses ergodic theory, uses dynamics. Okay, and this is a big field, is actually using ergodic theoretic tools to prove things in number theory. Okay, so I think today we will stop here.